Welcome back, and today I've got another fun experiment for you. What we're going to do is we're going to look at what happens to the weight of a rock when we put it underwater, and I think you're going to find the result rather surprising. But before we start, a story. When I was younger, I was brought up in a village and we were really lucky to have a river at the bottom of our fields. And so as children, we used to spend ages playing in it. And one of the things we absolutely loved to do was to get large rocks and build dams across the river. Now, one day my father explained to me that I could build a better dam by moving larger rocks. Well, that was pretty obvious. But what wasn't obvious is he said to me, if you get the larger rocks, if you can't lift them very easily, move them underwater and they'll be much easier to move. Well, this didn't seem to make sense because rocks don't float. But when we tried it, it really did work. They were much easier to move underwater than they were when we lifted them out into the air. So, what's happening here? So, it took a few years to find out what was going on. But of course I studied physics and learnt a little bit about Archimedes Principle and buoyancy. So what I'm going to show you is the fact that rocks really are much easier to move underwater. Right, time for an experiment. I've got my spring balance and I've checked it's correctly zeroed, and I'm just going to hang the rock off the spring balance, and it has a weight of about 1.7 newtons. That's 170 grams. We can forget about the string, it doesn't really play any part in this experiment. But what we're going to do is watch the plunger on the spring balance and see what happens when we submerge the rock in the water. Right, let's do the experiment. So I'm going to hold the rock over the water, and to make it a bit easier, I'll put my fingernail on the pointer on the spring balance, and then I'll lower the rock into the water. And I think you'll notice that if I hold it still, the rock appears to have got quite a bit lighter. But of course, one wonders what happens when you take the rock out again. So I'll lift the rock out, and I think you'll notice that we're back to where we started. So this is going to take some explaining. So I'm going to repeat the experiment with the camera a little bit closer, but look carefully at the spring balance. I've got my fingernail against the reading whilst the rock's out of the water, and now I'm going to submerge the rock, and you'll notice the reading of the weight becomes less. And if I keep my finger in the same place, as I take it back out of the water, the spring balance goes back to its original, slightly higher reading. So, my father really was right, that rocks, and other objects for that matter, really do feel lighter underwater. Now, I'm sure some of you know about this already. I'm old enough to have learnt to swim in a swimming pool that was open air at school, and one of the games we enjoyed playing was diving for a pool brick. The teacher used to throw the pool brick in, it's a sort of building brick covered in rubber. We used to dive down, bring the brick up to the surface and lift it onto the side of the pool. And if you've ever done that, you'll notice it's quite easy to bring the brick up through the water. The bit that's particularly difficult is lifting it out of the water and onto the side of the pool. And it's very similar to this, that the brick's easier to move when it's underwater. So the explanation here is not a particularly easy one, but I'll have a go. Of course, it was Archimedes, as you probably know, who realised what was going on here. And the first way to look at it is that if you put the stone or the rock into the water, the rock goes down, but the important bit is the water lifts up. And that water has been lifted up from where it was before and is trying still to push down. But actually, it's a little bit more complicated than that. Now, I hope you've seen my video on pressure at depth, the leaky can. That's the one where I take a cylindrical can, fill it with water, and there's a hole near the top, at the middle, and at the bottom. And because there's a huge weight of water on the bottom, you get a jet that goes further, you get a higher pressure. And higher up in the water, there's less water above, so the pressure is lower. And this is key to why the rock feels a little bit lighter when you put it underwater. So this idea of pressure at depth is key to explaining this. If you think about it, if I put the rock into the water, the top of the rock is in low pressure water and the bottom of the rock is in high pressure water. You know that pressure is force over area, so on the top of the rock, the force per unit area is lower, and on the bottom of the rock, the force per unit area is bigger. So there's a bigger force pushing up on the bottom of the rock than there is pressing down on the top of the rock. And this we call the buoyant uplift. It's the upthrust acting on the rock. So if we put a rock underwater, we know there's a resultant force due to the water upwards on the rock, and that has the effect of making it appear slightly lighter and easier to move. Archimedes really understood this because he realised that the rock pushes out of the way a volume of water, that's the water that's been lifted up higher in the beaker, and the upthrust force will be equal to that weight of water. So, you've learnt a little bit today, I hope, about why rocks really genuinely are easier to move underwater. And you've learnt a bit about buoyancy and upthrust forces and Archimedes' principle. So, I hope you enjoyed that experiment, and I look forward to seeing you again next time.